of all, let us introduce ourselves. We are MSc in Physics 5th year 9th sem students and myself Dharmika M. Sharma. I am Dear Kusuma.
I am Ashwin.
I am Ganajyoti.
So today we are going to do verification of Malus Law.
The aim of the experiment is to determine the relationship between the intensity of the transmitted light through analyzer and the angle between the axis of polarizer and analyzer. Also to verify Malus law.
Before getting into the experiment, let us know what is Malus law. Malus law describes how the intensity of polarized light changes as it passes through an analyzer, which is essentially another polarizer. Now let us look into the theory part.
Most of the ordinary light sources like the sun, candlelight, electric bulb, etc. emit unpolarized light. In an unpolarized light, electric and magnetic field vectors vibrate in all possible directions perpendicular to each other and also perpendicular to the direction of propagation of light. Unpolarized light can be represented as shown in the figure. The unpolarized light can be considered to be composed of two linear orthogonal polarization states with complete incoherence. When unpolarized light is incident on an ideal polarizer, the intensity of the transmitted light is 1/2 of the incident light. Also, if the polarizer is rotated with respect to the incident light, there is no change in the irradiance of the transmitted light. That is, its intensity remains half of the incident light. Certain transparent materials such as nickel, tourmaline have its cells arranged in a straight line manner only in one direction and are capable of filtering and allowing light waves having vibrations only in one plane. Such materials are called polaroids. The plane of vibration of the transmitted light will be parallel to the path axis of polarizer. This is represented in the given figures. This phenomenon of filtering and producing light waves having vibration confined to one particular direction is called polarization. Malus law. When light falls on a polarizer, the transmitted light gets polarized. The polarized light falls on another polaroid called analyzer, transmits light depending on the orientation of its axis with the polarizer. The intensity of light transmitted through the analyzer is given by Malus law. This law describes how the intensity of light transmitted by the analyzer varies with the angle that its plane of transmission makes with that of the polarizer. The law can be stated in words as follows. The intensity of the transmitted light is proportional to the square of the cosine of the angle between the transmission axis of the polarizer and analyzer, that is theta. If A0 is the amplitude of the plane polarized incident light and AT is amplitude of the light transmitted through the analyzer, which is inclined at an angle theta with the polarizer as shown in the figure, then AT is equal to A0 cos theta and AT square is equal to A0 square cos square theta. If theta is equal to 0 degree, 180 degree or 360 degree, the second polarizer, that is the analyzer, is aligned with the first polarizer and the value of cos square theta equals 1. Thus the intensity transmitted by the second filter is equal to the light intensity that passes through the first filter. This case will allow maximum intensity to pass through. If theta equals 90 degree or 270 degree, the second polarizer, that is the analyzer, is oriented perpendicular to the plane of polarization of the first filter and the cos square theta equals 0. Thus no light is transmitted through the second filter. This case will allow minimum intensity, that is 0 intensity, to pass through. As intensity is directly proportional to amplitude square, IT is equal to AT square, which is equal to A0 square cos square theta, which is equal to I0 cos square theta, where IT is the intensity of the light transmitted through the analyzer and I0 is the intensity of the incident plane polarized light. The mathematical expression for Malus law is IT is equal to I0 cos square theta. The light intensity cannot be measured directly. The light energy is converted into electrical energy using photodetectors such as a photocell or light dependent resistor LDR. In such photodetectors, the current produced is directly proportional to the light intensity.
So now I hope everyone got a clear idea of the theoretical part of Malus law. Now let's look into the experimental part of it.
So now let's look into the experimental setup. The apparatus required for this experiment are
While moving to the apparatus part, the first apparatus which is required is the bench mount. Bench mount is also called as the optical bench, which is having 3 mounts. In these 3 mounts, laser light, polarizer analyzer pair and a photo detector are kept. The bench mount is of 50 cm length. The second apparatus which required is the laser source. Laser source is having 2 parts. First one is the laser light and the second one is the laser diode module. This laser diode module will pass polarized or unpolarized source of light which is having a wavelength of 650 nanometer and power 5 milliwatts. Next one is the most important apparatus which is required to this experiment, that is polarizer analyzer pair. We know what is a polarizer. Polarizer allows light vibrating only in a certain direction to pass through. And here analyzer is acting as a second polarizer which can be rotated at different angles. We can rotate this analyzer up to 360 degrees. Analyzer is used to analyze the light which is passing through it. Fourth one is the photodetector. Photodetector is an apparatus which will detect the light which is transmitted from the analyzer, and then it will convert this detected light into a current, and then it will pass through the laser power meter. Last one is laser power meter. Laser power meter is used to measure the output. Output is the amount of intensity of the light transmitted by the analyzer in terms of milliwatts. Now we will move on to the application part of this experiment. Actually, Malus Law is having so many real-life applications. First of all, we will use it in sunglass and camera filters. We will use this in LCD, liquid crystal display screens. Then we will use Malus Law for reduction of the glare on car windows. Then we will also use this Malus Law in remote sensing and satellite imaging.
Okay, now we'll look into the procedure. Okay, now I am going to on the source for the laser. And from here, the laser rays is falling. And this is polarizer analyzer pair. And this is a photodiode which is sensing the laser ray. And this is the meter used for the measurement of the intensity of laser. So in this experiment what we are going to do is, we'll on the laser, and this laser polarizer analyzer pair and this photodiode should be in a parallel such that this laser ray should fall on this photodiode. Then only we will be able to see the intensity of the light. See, when exactly this laser light is falling on the center, we are able to see the intensity. Now what we need to do is, we have to keep this analyzer polarizer pair in the distance 20 cm from this pair, and then we will be having from 0 we have to rotate the angle till we get the maximum intensity. Now the intensity is 0.33 for 80 degrees, and then we have to measure till we get the maximum intensity. So now for 140 degrees we are getting the intensity of 1.51, that is the maximum. So our theta naught is 140 degrees. Now from this 140 degrees, for every 10 angles we have to take the intensity. Now for 150 it is 0.35, and the angle we have to change, and we have to note down the intensity for till 360 degrees. Now we have set the intensity for 20 centimeter. Now we have to change this polarizer analyzer pair to other distance that we are taking as 25 centimeter. Now the polarizer analyzer pair is at 25 centimeter. Now we have to repeat the same steps and obtain the theta max and the theta.
Okay, now we'll see the calculation and observation part of this experiment.
Let's see the observation and calculation part. In this experiment, we recorded the intensity when the light passes from the analyzer and the polarizer.
Initially, we kept the distance as 20 centimeters between the analyzer and the polarizer, where we recorded the maximum angle as 150 degrees and the corresponding intensity as 3.23. In the second column, we recorded theta minus theta naught, which represents the difference between the angle and the maximum angle. And third column, we saw cos square of theta minus theta naught and then intensity corresponding to that angle. In the same way, we recorded the intensity when we took the distance as 25 centimeters between the analyzer and the polarizer. Here, we received our maximum angle has 150 degrees and maximum intensity has 3.48. Then we plotted the graph for those readings. Initially, we took intensity versus cos squared theta minus theta naught graph, and other form of graph is intensity versus theta minus theta naught. So the first graph we'll get is cosine graph, and one more graph is the straight line. In the same way, for the distance 25 centimeters, we'll get one straight line and one more is a cosine graph. So here the relative intensity of the light emerging from the analyzer is maximum at 0 and 180. As we saw, the peaks were maximum at 0 and 180 and it attains the minimum value at 90 and 270. And the second form of graph which we drawn has intensity versus cos square theta minus theta naught. It gives a straight line which represent the correctness of the Malus law.
Hence, the Malus law is verified. It is a simple but powerful demonstration of polarization in optics.
Hope you all have understood.
Thank you for watching.